Hey everyone, have you ever wondered how we actually know what industrial facilities are releasing into the air? We hear about emissions targets and regulations all the time, but the truth is, none of those policies matter without incredibly precise, highly regulated monitoring equipment. Welcome to this explainer, where we're going to unpack EPA Performance Specification 6, or PS-6 for short. Think of PS-6 as the ultimate lie detector test for environmental monitoring systems at stationary sources. It's the rigorous set of standards that ensures the equipment tracking pollutant mass emission rates is telling the truth, the whole truth, and nothing but the truth. Okay, let's dive into our procedural playbook for this explainer. We're going to cover measuring emissions basics, what exactly a CERMS is, the calibration drift test, the relative accuracy test, and finally, how to crunch the final numbers. Let's get to it.
Section 1. Measuring emissions. The basics. Because hey, before we can test any equipment in the field, we really got to understand the ground rules, right?
PS-6 doesn't just exist in a vacuum, and it definitely doesn't try to reinvent the wheel. Actually, it relies heavily on an older, foundational regulation known as Performance Specification 2, or PS2. Think of PS2 as your operational bedrock. If you're installing a monitoring system, PS6 points directly to PS2 for the exact specs on where to put your equipment, where to take measurements, how to run the test procedures, and even how to handle the core data analysis. PS6 is essentially an extension of that solid groundwork.
All right, moving into Section 2. What is a CERMS? Let's translate some of that government speak and define the actual piece of technology we're evaluating today.
So, CERMS. It stands for a Continuous Emission Rate Monitoring System. The absolute key phrase you want to focus on here is total equipment. We aren't just talking about a single lonely probe shoved into a smokestack. No, we're evaluating the entire interconnected system required to determine and record the pollutant mass emission rate. And crucially, it measures this in terms of mass per unit of time, like kilograms per hour. This system is literally the central hub. It's the heart of stationary source environmental compliance.
Now, inside that entire CERMS setup, you've got some specific, vital organs. The most critical one, highlighted in PS6, is the flow rate sensor. This little guy senses the volumetric flow rate, basically the speed and volume of the gas moving through the stack, and generates an output proportional to that flow. But here's the kicker. It absolutely must have provisions to check its calibration drift individually for each parameter it measures, like velocity or pressure. It needs its own targeted health check.
Pitting calibration drift against relative accuracy really brilliantly illustrates the core of Performance Specification 6. To prove a CERMS is actually reliable, it has to pass two major exams. First up is calibration drift, or CD, which just checks if the system stays perfectly zeroed out over time. Second is relative accuracy, or RA, which checks if the system's measurements actually match up with a proven external standard. These two tests, they're the absolute bread and butter of PS6.
Real quick, if you're enjoying this structured breakdown of environmental monitoring and want to keep mastering complex regulations just like this one, make sure to hit that subscribe button right now. Seriously, it's the best way to ensure you never miss another crucial compliance explainer from us. All right, back to the tests.
Section 3, the Calibration Drift Test. It is time to transition from our definitions straight into the fieldwork.
So, the calibration drift test procedure is fundamentally about stability. Think of it like stepping on a bathroom scale. Before you trust the weight it gives you, you want to make sure it naturally sits at 0. To test the CERMS, we introduce specific reference signals. A low signal, which is 0 to 20% of full scale, and a high signal, which is 50 to 100%. We record exactly how the CERMS responds to these known inputs, and then we subtract that response from the true reference value to see how far off it is. Oh, and if the system automatically adjusts itself, this test has to be done immediately before those adjustments happen, just to capture the true uncorrected drift.
Which brings us to a very important number, 3. For the flow rate analyzer, the calibration cannot drift or deviate by more than 3% of the high-level reference value over the test period. And under PS6, that test period is typically a full 7 days. So, if your flow rate sensor wanders off by more than 3% over a week, it fails the drift test, period. It simply means the system is not stable enough to be trusted for regulatory compliance.
Section 4. The relative accuracy test. Because, a system can be perfectly stable but still be consistently wrong. Let's look at the second exam.
The relative accuracy test protocol is where we see how accurate the system is compared to a totally independent, proven standard. The sampling strategy here? It relies on PS2 again. And fun fact, you can actually run this accuracy test at the exact same time you're running your 7-day calibration drift test. Talk about multitasking.
To prove the CERMS is telling the truth, it is pitted against established reference methods, or RMs. For volumetric flow rate, the EPA specifies highly manual, rigorous reference methods like Method 2, 2A, 2B, 2C, or 2D. Basically, we take the automated CERMS reading and compare it directly to these meticulous manual benchmarks.
And that brings us to our next hard threshold, 20. The regulations strictly dictate that the relative accuracy of the CERMS can be no greater than 20% of the mean value of the reference method's test data. If your automated system is deviating by more than 20% from the manual benchmark, yeah, it goes back to the drawing board. It's so vital to remember that these systems are tracking total mass emissions per unit of time, so being off by a wide margin could literally mean thousands of pounds of unaccounted pollutants.
Section 5, crunching the final numbers. Let's move on and see how this all builds into the actual documentation facility managers have to submit.
The official documentation outlines exactly how the pass-fail data is logged in the real world. You've got your test run number, the exact date and time, and then that crucial side-by-side comparison, the emission rate determined by the CERMS right next to the rate determined by the manual reference methods. Finally, the exact difference between the two is calculated. But here is a massive detail to remember. You cannot compare apples to oranges. All this data must be corrected to a consistent basis. That means you absolutely have to account for exact moisture, temperature, and pressure conditions before you lock in these final numbers.
Look, I know, Performance Specification 6 might just look like a dense wall of technical jargon and math, but at its core, it's a shield. So I want to leave you with this. If a CERMS fails to monitor emissions accurately, if it drifts past 3% or totally misses that 20% accuracy mark, what are the hidden impacts on our environment and our public health? Ultimately, strict enforcement of these invisible monitoring systems is what keeps our air clean and our industries accountable. Thanks so much for joining me on this explainer, and I'll see you in the next one.